All right, so if this is the basic idiom for implementing recursive programs in MapReduce, maybe we're done. Well, there's a couple of problems here. And here they are. First, on every iteration, right, we're going to do this over and over and over again as we traverse the graph. And the number of times we're going to traverse the graph is actually the diameter of the graph, which we talked about. Well, on every iteration, we're going to process all billion edges in the graph in the map phase and shuffle them across the network to the reduce phase in order to compute this join. This wasn't so bad if you're only going to do this once, but if you're going to do it every time, there's no useful work happening in this map phase. You're just reading the edges off disk, assigning the key to the, identifying the join key, emitting the appropriate tuples, and sending across the network to the reduce phase, implementing a standard join in MapReduce, which we did as part of the homework. So this is extremely wasteful. The second point, which is a little bit more subtle, is that the answer set, AI, is growing at every iteration, right? You find more and more answers, and as soon as you stop finding answers, you're done. Well, this is getting bigger and bigger and bigger over time, so it's not completely static. But all the old values that you've already seen before are read off of disk and shuffled across the network in the same way in order to try to remove duplicates. And if you've already done that once, you shouldn't have to do it again. So the solution here is to fill in some sort of a cache on the reducer side of the MapReduce program. So instead of shuffling this across the network, we're going to shuffle it once in the first iteration and then read it off of disk in the second iteration. And with a variant of this trick, you can do the same thing here, where you'll read it off of disk and then append more new tuples back to the same cache right as you're done. And with some careful thought, you can arrange for this to happen within the MapReduce framework. Sorry, not within, by extending the MapReduce framework, and still keep a MapReduce programming interface. And this is what we did as part of our research for this system called Hadoop, which is to add iterative capabilities to the Hadoop MapReduce system. Okay, and one of the applications that we did with this was to implement data log. All right, and so this makes a pretty big difference. So this is a plot of runtime, and this is iteration number. So this is just the time it takes to do each iteration. And without the cache that we just described, every iteration takes about the same amount of time in this particular data set, which was a variant of the same one you processed in the Elastic MapReduce assignment. With the cache, the first iteration actually takes a little longer because we have a little bit more work to do. We have to prepare this cache. But subsequent iterations take far, far less time because you don't have to map and shuffle that huge edge relation across the network anymore. So this ended up being, well, really arbitrarily faster because the more iterations it takes, the better and better, the more and more difference it gets in the overall runtime. With the variant of that trick to also optimize the duplicate elimination step, plus another set of optimizations that had to do with using the MapReduce framework in sort of an intelligent way, we're able to sort of get this pretty horrible performance for raw vanilla MapReduce on iterative programs and get it way down to something that is actually kind of approaching the raw overhead of just running a Hadoop job. Meaning, you do no useful work with the Hadoop job. You just launch a task on every machine in the cluster and do no useful work and then shut down. Okay, and that's what this bottom line is. So what I think the takeaway here is, one is I just want you to internalize that trick, but the other thing is if you're using raw Hadoop, if you're using, I shouldn't say raw, if you're using MapReduce right out of the box, it's not great for iteration, mainly for this reason. There's actually a few other optimizations we explored in a couple of papers, but this is the one that makes the most difference, is the fact that there's quite frequently there's going to be loop invariant data that you need to process, and just to wastefully reprocess it on every iteration turns out to be a killer. Okay. And then one more point I want to make about this before we move on is that the number of new tuples discovered, the new results discovered on every iteration, tends to have a pretty standard pattern, which is a result of the degree distribution of common graphs found in practice, which we talked about in the histogram segment a little while ago. So this plot is on the y-axis is the number of new results discovered, and the x-axis is the iteration number. And what you can see here is that in the first few iterations, you quickly start to find an enormous number of new results. Right? And notice this is a log scale, so this difference is really, really huge. But then pretty soon it tapers off, and you're just kind of piddling along, finding smaller and smaller sets of new results, but you're not done yet either. You're still finding new stuff, but you're not finding much new stuff. So this is really, really rough for MapReduce, because every one of these iterations, way out here in this long tail, this end game, as Frade and Ullman called it in a paper, you still have to pay the overhead of launching Hadoop on a huge cluster and sort of processing and checking for things, even though you don't actually find that many more results, right? Most of the results you've already discovered. So, fine, that's one point. The other point here is that this does make sense, because what you're doing is you quickly get to this. Within a few iterations, you're going to get to this middle part of the graph that's connected to everything, and the fan out is huge, and you've discovered everything. You're going to hit one of these really popular vertices that's connected to everything, and then once you're past that, you've pretty much seen everything you're going to see, and you quickly taper off. Okay, so one thing to think about is what to do about these two different regimes you're in. One regime where you're doing a lot of useful work, and one regime in this end game where you're not doing very much useful work. And there's a couple of things you can think about here. One is, it may not be unreasonable to just stop processing when you are no longer producing that many results. This would produce the wrong answer according to the program, but it might be reasonable in a lot of cases. If you're mostly looking for an approximation, you can get a pretty good approximation after the first several iterations. This extra work is not doing you that much good. Another approach would be to scrap MapReduce and try to find something that had less overhead on a per iteration basis. And so there's a system that, for example, we're working on now that doesn't have this property, right? The runtime is sort of proportional to the number of tuples discovered, as opposed to having this very large fixed cost just to launch a job at all, which is a problem with Hadoop. Still another way is perhaps to change strategies. In this regime, you process it as we've described. In this later regime, you actually might try to do more work per iteration. For example, don't bother checking for duplicates, because you're only finding 100 new tuples anyway. Why bother even checking for duplicates? Just keep going and going and going and going for a while to save the number of MapReduce jobs you have to do. And so we've explored these various options, and they all work to varying degrees. Okay.